Structural realism is considered by many realists and anti-realists alike as the most defensible form of scientific realism. There are different forms of structural realism and an extensive literature about their pros and cons, and how they relate to case studies from science and its history. There are connections with debates in metaphysics, philosophical logic, and philosophy of mathematics. This entry is a comprehensive survey of the field. 1. Introduction. Scientific realism requires belief in the unobservable entities posited by our most successful scientific theories. It is widely held that the most powerful argument in favor of scientific realism is the no miracles argument, according to which the success of science would be miraculous if scientific theories were not at least approximately true descriptions of the world. While the underdetermination argument is often cited as giving grounds for skepticism about theories of unobservable entities, arguably the most powerful arguments against scientific realism are based on the history of radical theory change in science. The best known of these arguments, although perhaps not the most compelling of them, is the pessimistic meta-induction, according to which reflection on the abandonment of theories in the history of science supports the expectation that our best current scientific theories will themselves be abandoned, and hence that we ought not to assent to them. Structural realism was introduced into current philosophy of science by John Worrall in 1989, as a way to break the impasse that results from taking both arguments seriously and have the best of both worlds in the debate about scientific realism. With respect to the case of the transition in 19th century optics from Fresnel's elastic solid ether theory to Maxwell's theory of the electromagnetic field, Worrall argues that there was an important element of continuity in the shift from Fresnel to Maxwell, and this was much more than a simple question of carrying over the successful empirical content into the new theory. At the same time, it was rather less than a carrying over of the full theoretical content or full theoretical mechanisms, even in approximate form. There was continuity or accumulation in the shift, but the continuity is one of form or structure, not of content. According to Worrall, we should not accept standard scientific realism, which asserts that the nature of the unobservable objects that cause the phenomena we observe is correctly described by our best theories. However, neither should we be anti-realists about science. Rather, we should adopt structural realism and epistemically commit ourselves to the mathematical or structural content of our theories. Since there is, says Worrall, retention of structure across theory change, structural realism both A. avoids the force of the pessimistic meta-induction by not committing us to belief in the theory's description of the furniture of the world, and B. does not make the success of science, especially the novel predictions of mature physical theories, seem miraculous, by committing us to the claim that the theory's structure, over and above its empirical content, describes the world. Worrall's paper has been widely cited in an extensive literature in which various varieties of structural realism are advocated or criticized, and different notions of structure are discussed. These contemporary debates recapitulate the work of some of the greatest philosophers of science of the late 19th and early 20th centuries. The increasing mathematization of physics through the 19th century, with electromagnetism and thermodynamics lacking mechanical and material models, and then the advent of quantum and relativity physics, prompted a variety of structuralist responses. Worrall says he found his structural realism in Henri Poincaré, whose structuralism was combined with neo-Kantian views about the nature of arithmetic and group theory, and with conventionalism about the geometry of space and time. Hernan McMullen argues that Pierre Duhem was a realist about the relations found in laws, but not about explanations in terms of an ontology. According to Worrall, Barry Gower, and Elie Zahar, Duhem, too, was a kind of structural realist, though there are passages in Duhem that more readily lend themselves to an instrumentalist interpretation. See the entry on Pierre Duhem. Milena Ivanova compares the thought of Duhem and Poincaré in respect of conventionalism and structural realism, identifying significant differences between their views as well as similarities. Gower's historical survey of structural realism discusses how it figures in the thought of Ernst Cassirer, Moritz Schlick, Rudolf Carnap, and Bertrand Russell. Stathis Silos explores the connections between structuralism and the Ramsey sentence approach to scientific theory in the development of Carnap's philosophy from logical positivism to ontologically relativist empiricism. Other important pioneers of structuralism about science include Arthur Eddington, Grover Maxwell, and Herman Weyl. Ladyman distinguished epistemic and ontic forms of structural realism in arguing for the latter. Many of those who have taken up structural realism have been philosophers of physics who have developed various forms of ontic structural realism, most notably Stephen French. Others, including Worrell, have made it clear that their structural realism is a purely epistemological refinement of scientific realism. On the other hand, Bas van Freysen defends an empiricist and non-realist form of structuralism about science, based on his view of scientific representation and motivated by an illuminating reconstruction of the origins of structuralism in the debate about the epistemology of physical geometry in the 19th century. Other kinds of structuralism abound in current analytic philosophy. These include causal structuralism concerning the individuation of properties, mathematical structuralism concerning the nature of mathematical objects, and structuralism about laws and dispositions. Following the debates about structural realism in the philosophy of science in the early 20th century, the notion of structure in general and the idea of modal structure in particular have also become prominent in analytic metaphysics. Clearly, there are many different notions of structure and many different kinds of structural realism. This article reviews the main issues and provides a guide for further reading. 2. The best of both worlds. Scientific realism became dominant in philosophy of science after the demise of the forms of anti-realism about science associated with the logical positivists, namely semantic instrumentalism, according to which theoretical terms are not to be interpreted as referring to anything, and theoretical reductionism, according to which theoretical terms are disguised ways of referring to observable phenomena. These forms of anti-realism rely upon discredited positivist ideas about scientific language, such as that it can be divided into theoretical and observational parts, that much of it should not be taken literally, or that its empirically surplus content is redundant. Bas van Freysen revitalized the debate about scientific realism by proposing his constructive empiricism as an alternative. His anti-realism is skeptical rather than dogmatic, and does not depend on the distinction between theoretical and observational terms. He allows that terms such as subatomic particle and particle too small to see are perfectly meaningful and should be taken literally. The former term is theoretical, and the latter term is not, but both purportedly refer to unobservable entities. On the other hand, he holds that it is perfectly rational to remain agnostic about whether there are any such particles, because he argues that to accept the best scientific theories we have only requires believing that they are empirically adequate, in the sense of correctly describing the observable world, rather than believing that they are true simpliciter. How then are we to decide whether to believe in the full theoretical truth of scientific theories, including what they say about unobservable entities such as electrons and black holes, or whether to believe instead only that our best scientific theories are empirically adequate? Van Freysen argues that since the latter belief is logically weaker and yet as empirically contentful as the former belief, it is natural for an empiricist to go only as far as belief in empirical adequacy. On the other hand, many philosophers are moved by the fact that belief in only the empirical adequacy of our best scientific theories leaves us unable to explain the phenomena that they describe. Inference to the best explanation is widely believed to be an important form of reasoning in science, and the production of explanations of the world is often supposed to be one of the main successes of science. When the target of explanation becomes science itself, and its history of empirical success as a whole, we arrive at the no miracles argument famously presented by Hilary Putnam as follows.
The positive argument for realism is that it is the only philosophy that doesn't make the success of science a miracle.
The no miracles argument is elaborated in terms of specific features of scientific methodology and practice. Richard Boyd argues that in explaining the success of science, we need to explain the overall instrumental success of scientific methods across the history of science. Alan Musgrave says that the only version of the no miracles argument that might work is one appealing to the novel predictive success of theories. Some realists, such as Silos, have gone so far as to argue that only theories which have enjoyed novel predictive success ought to be considered as falling within the scope of arguments for scientific realism. Colin Howson, P.D. Magnus, and Craig Callender, and Peter Lipton argue that the no miracles argument is flawed, because in order to evaluate the claim that it is probable that theories enjoying empirical success are approximately true, we have to know what the relevant base rate is, and there is no way we can know this. Magnus and Callender argue that wholesale arguments that are intended to support realism about science as a whole are only taken seriously because of our propensity to engage in the base rate fallacy of evaluating probabilities without knowing all the relevant information. They think we ought to abandon the attempt to defend scientific realism in general rather than on a case-by-case basis. This assumes that the wholesale arguments against scientific realism do not work. Of these, the underdetermination argument, according to which the existence of empirical equivalents to our best scientific theories implies that we should withhold epistemic commitment to them, is as often dismissed by realists as generating doubt about unobservables that is no more worrying than doubting other minds or the external world. They argue that since scientists find ways of choosing between empirically equivalent rivals, philosophers ought not to make too much of merely in-principle possibilities that are irrelevant to scientific practice. The power of the arguments against scientific realism from theory change is that, rather than being a priori and theoretical, they are empirically based, and their premises are based on data obtained by examining the practice and history of science. Ontological discontinuity in theory change seems to give us grounds not for mere agnosticism but for the positive belief that many central theoretical terms of our best contemporary science will be regarded as non-referring by future science. So-called pessimistic meta-inductions about theoretical knowledge take many forms and are probably almost as ancient as skepticism itself. They have the basic form. Proposition P is widely believed by most contemporary experts, but P is like many other hypotheses that were widely believed by experts in the past and are disbelieved by most contemporary experts. We have as much reason to expect P to befall their fate as not. Therefore, we should at least suspend judgment about P if not actively disbelieve it. More precisely, Larry Laudan gave a very influential argument with the following structure. 1. There have been many empirically successful theories in the history of science which have subsequently been rejected and whose theoretical terms do not refer according to our best current theories. 2. Our best current theories are no different in kind from those discarded theories, and so we have no reason to think they will not ultimately be replaced as well. So by induction, we have positive reason to expect that our best current theories will be replaced by new theories according to which some of the central theoretical terms of our best current theories do not refer, and hence we should not believe in the approximate truth or the successful reference of the theoretical terms of our best current theories. The most common realist response to this argument is to restrict realism to theories with some further properties so as to cut down the inductive base employed in point 1. Moreover, Peter Lewis, Mark Lang, and Magnus and Callender regard the pessimistic meta-induction as a fallacy of probabilistic reasoning. However, there are arguments from theory change that are not probabilistic. Note first that there are several cases of mature theories which enjoyed novel predictive success, notably the ether theory of light and the caloric theory of heat. If their central theoretical terms do not refer, the realists' claim that approximate truth explains empirical success will no longer be enough to establish realism, because we will need some other explanation for the success of the caloric and ether theories. If this will do for these theories, then it ought to do for others where we happen to have retained the central theoretical terms. And then we do not need the realists' preferred explanation that such theories are true and successfully refer to unobservable entities. Laudan's paper was also intended to show that the successful reference of its theoretical terms is not a necessary condition for the novel predictive success of a theory, and there are counterexamples to the no miracles argument. A successful reference of its central theoretical terms is a necessary condition for the approximate truth of a theory. B. There are examples of theories that were mature and had novel predictive success, but whose central theoretical terms do not refer. C. So there are examples of theories that were mature and had novel predictive success, but which are not approximately true. D. Approximate truth and successful reference of central theoretical terms is not a necessary condition for the novel predictive success of scientific theories. There are two common responses to this. 1. Develop an account of reference according to which the abandoned theoretical terms are regarded as successfully referring after all. Realists developed causal theories of reference to account for continuity of reference for terms like atom or electron, even though the theories about atoms and electrons have undergone significant changes. The difference with the terms ether and caloric is that they are no longer used in modern science. However, as C.L. Hardin and Alexander Rosenberg argue, the causal theory of reference may be used to defend the claim that terms like ether referred to whatever causes the phenomena responsible for the term's introduction. This is criticized by Loudon as making the reference of theoretical terms a trivial matter, since as long as some phenomena prompt the introduction of a term, it will automatically successfully refer to whatever is the relevant cause. Furthermore, this theory radically disconnects what a theorist is talking about from what she thinks she is talking about. For example, Aristotle or Newton could be said to be referring to geodesic motion in a curved spacetime when, respectively, they talked about the natural motion of material objects and the fall of a body under the effect of the gravitational force. 2. Restrict realism to those parts of theories that play an essential role in the derivation of subsequently observed, novel predictions, and then argue that the terms of past theories, which are now regarded as non-referring, were non-essential, and hence that there is no reason to deny that the essential terms in current theories will be retained. Philip Kitcher says that no sensible realist should ever want to assert that the idle parts of an individual practice, past or present, are justified by the success of the whole. The most detailed and influential response to the argument from theory change is due to Psillos, who combines strategies 1 and 2. Ha-Seok Chang, Kyle Stanford, Mohammed El-Samahi, and Timothy Lyons criticize Psillos's account. Other responses include Kitcher's model of reference, according to which some tokens of theoretical terms refer and others do not. Christina McLeish criticizes Kitcher's theory by arguing that there are no satisfactory grounds for making the distinction between referring and non-referring tokens. McLeish argues that abandoned theoretical terms like ether partially refer and partially fail to refer. Juha Satsi denies premise A and claims that there can be approximate truth of the causal roles postulated by a scientific theory without its central terms necessarily successfully referring. There is no consensus among those defending standard realism in the face of theory change by adopting the selective approach of 2 with an account of reference. Consider again the much-discussed case of the ether. Psillos argues that Fresnel's use of the term ether was essential to his successful theorizing, but that it referred to the electromagnetic field. Worrall argues that the project of defending realism by securing reference for abandoned theoretical terms is missing the point of the problem as well as the key to its solution. It is plausible to take field to be a new way of referring to what the ancients and early moderns termed ether or ether. Fields like the ether permeate all of space and are posited to explain optical, magnetic, and other phenomena. Anaxagoras is said to have introduced the idea of the ether to propel the planets, and subsequently there were many ethers to account for various things. Fresnel's optical ether was supposed to be a solid, and Maxwell's field behaves very differently, and is said to be immaterial. However, from our current perspective, the ether has much more in common with the field than atoms do with the indivisible particles of antiquity, and so continuity of reference is not the issue. The reference of the term energy at least overlaps in classical and quantum theories because quantities in each coincide in the limit as the number of particles increases. This does not solve the problem that the radical ontological and metaphysical differences between the theories pose for the realist. Different theories often use the same terms to say very different things about what the world is like. The question of which terms refer does not settle the whether it is plausible to say that the metaphysics and ontology of the theory is even approximately true, because in many cases the same theoretical term is still used despite radical changes. The argument from theory change threatens scientific realism because if what science now says is correct, then the ontologies of past scientific theories are far from accurate accounts of the furniture of the world. If that is so, even though they were predictively successful, then the success of our best current theories does not mean they have got the nature of the world right either. The task of providing an adequate theory of approximate truth that fits the history of science and directly addresses the problem of ontological continuity has hitherto defeated realists. But a much more tractable problem is to display the structural commonalities between different theories. Hence, a form of realism about the structure of theories might not be undermined by theory change. Gerhard Schertz proves a structural correspondence theorem showing that successive theories that share empirical content also share theoretical content. The structuralist solution to this problem is to take the metaphysical import of successful scientific theories to consist in their giving correct descriptions of the structure of the world, where this structure can be captured with different ontologies. Theories can be so different as to be contrary to each other, while both represent the same structure in the phenomena. Consider the theory according to which combustion is the emission of phlogiston that was dominant in chemistry prior to the end of the 18th century. Despite their radical disagreement about the nature of combustion, both phlogiston theory and the oxygen theory of Lavoisier that succeeded it regard combustion, respiration, and the calcination of metals as the same kind of process and reciprocal to another kind of process exemplified by the smelting of ore. Furthermore, there are tables of affinity that were formulated by the phlogistonists that can be reinterpreted in terms of Lavoisian chemistry. Hence, even in this case, there is continuity of structure despite the central entity of the old theory not existing at all according to the new theory. There are numerous examples of continuity in the mathematical structure of successive scientific theories. Indeed, the principle that old ones should be recovered from new ones in some limit was explicitly formulated by Niels Bohr as the methodological principle known as the correspondence principle, according to which quantum mechanical models ought to mathematically reduce to classical models in the limit of large numbers of particles, or in the limit of Planck's constant becoming arbitrarily small relative to the action of the system. There are many cases in quantum mechanics where the Hamiltonian functions that represent the total energy of mechanical systems imitate those of classical mechanics, but with variables like those that stand for position and momentum replaced by Hermitian operators. There is now a large literature in philosophy of physics that considers different characterizations of the structure of theories and how it relates to the relations between them and their empirical content. Simon Saunders discusses the structural continuities between classical and quantum mechanics and also shows how much structure Ptolemaic and Copernican astronomy have in common. Harvey Brown explains the correspondence between special relativity and classical mechanics. Jonathan Bain and John Norton discuss the structural continuity in descriptions of the electron, as does Angelo Che. Votsis considers examples of continuity and discontinuity in physics. Robert Batterman discusses many examples of limiting relationships between theories, notably the renormalization group approach to critical phenomena and the relationship between wave and ray optics. Holger Lyer extends Worrell's original example of the continuity between wave optics and electromagnetism by considering the relationship between Maxwellian electrodynamics and quantum electrodynamics. Alisa Bokulich considers the quantum classical transition in detail, arguing for what she calls interstructuralism as an approach to intertheory relations that emphasizes structural continuities and correspondences. Zenker and Gardenfors adopt a conceptual spaces approach to the continuity of theory structure. Joshua Rosler analyzes intertheory relations in physics, arguing that local relations between models in different domains must be considered as well as global relations between theories. Monero argues for the stability of Lie algebras over theory change in physics. The most minimal form of structuralism focuses on empirical structure, and as such is best thought of as a defense of the cumulative nature of science in the face of Kuhnian worries about revolutions. See Catherine Brading's and Elaine Landry's Minimal Structuralism and Otavio Bueno's and Van Friesen's Structural Empiricism.